purpose of this video is to talk to you about Chapter 7, which is all about sampling and sampling distributions. So today I'm going to try a different method and we'll see how it works. The drawing before was a little bit cumbersome, so I'm going to try a new method today. So sampling and sampling distributions being the topic of the day, we have several objectives. So first of all, I want you to be able to explain some of the common sampling biases, and then related to that, be able to describe sampling methods, a sampling distribution, and how that relates to the sample mean. And then you should be pretty comfortable with the central limit theorem and using the central limit theorem to describe the sampling distribution. So first, let's just talk a little bit about the importance of sampling. You know, sampling in statistics is a little bit like the offensive line is to the quarterback in football. And what I mean is, if you don't have good data, you cannot have good statistics. You might have done all the methodology correct, but what it yields for you is useless. So the same is really true with a quarterback, right? Because the quarterback could be the best quarterback in the world, but he cannot do anything if he doesn't have a line blocking for him. So we say in statistics that good data is critical in statistics. And actually, good data is just like the offensive lineman is to a star quarterback. So there's a few things you've just got to get down. All data is not created equally. You have to understand that you need data that relates to the population with which you wish to generalize your study to. So if you're a doctor and you would like to generalize your study back to a population of elderly people, then you should use elderly people in your study. And as simple as that sounds, let me tell you, it is so often a problem in all kinds of statistical studies. So the population, the term the population, is what we're trying to show. It is the population of interest. It should be represented in your sample. Your sample is the subset of the population, but the population, of course, should be still representing your sample should, of course, be representing your population. When we don't have a representative sample, then we say that we encounter something called statistical bias, which is a systematic under or overestimating of our population parameter. So an example of bad samples and inaccurate results can be seen here on this little quick video I have for you.
Very simple but powerful historical example that illustrates why this is the case. During World War II, the British were losing a lot of their bombers over Germany, so they decided to add armor to their planes. Now the armor was heavy and expensive, so they decided that they'd only add it to the parts of the plane that were most critical. Luckily, when planes returned from their bombing runs, they kept meticulous record where they had been shot. So they were able to take all of these diagrams and superimpose them in order to get a good sense of where the planes were being hit by German anti-aircraft fire. When they did this, there was a very clear picture that emerged. The planes had holes in the wings, the nose, and the tail. So they decided that they would add more armor there. Before they did, however, they brought in an Austrian economist named Abraham Wald, who took one look at the data and said that this is the exact opposite thing that you want to do. The planes they used to generate the diagrams were the planes that had returned from their bombing runs. So the planes that had been shot down were being shot in the two areas that did not have any holes, the body and the rudder. The British added armor to those two areas instead, and thousands of British lives were saved. This is a classic econometric example illustrating the importance of identifying and controlling for selection bias, but there's a broader point to be made. It's critically important to ensure that you're using the right methodology to measure, or
So I think that video does a good job of showing why we care about such things as the sample. Of course, you have to consider your sample. So here we have just a quick summary of why the sample matters and sort of some basics about it. Okay, so it needs to be a good representation of this body that you are trying to inform, right? So a good representative sample is hard to find. It absolutely is hard to find, and it is fabulously important. And it's necessary that our sample has 3 characteristics. So first, we want the sample to be representative of some larger group, randomly generated and proportioned. Textbooks like to use colored marbles to pick out of an urn or whatever. The problem is life is so much more complex than an urn full of marbles. And then another thing we want to make sure we have is we want to see if our sample is somehow comparable. Could we compare group 1 to group 2? Because that makes our sample so much more reliable. And then the third thing is data. If we can get our data to span across time, we can learn so much more about our population than we could otherwise. We call this data longitudinal data. So longitudinal data is said to be sort of the Audi Quattro, if you will. I like Audi Quattros, so I think they're great cars. It's kind of the Audi Quattro of data, meaning it is the best, richest data that we can have. There are many, many, many examples of longitudinal studies that have been used for all kinds of studies over time. For example, there's this Framingham longitudinal study of about 2,000 people, and they looked at the relationship between smoking, eating, exercise, weight, diet, and all this stuff, and mortality rates at these people over like 60 years. And they call it the Framingham longitudinal study because it was done in Framingham, Massachusetts. But anyways, this study alone has been used for some 3,000 or 4,000 different research articles over time. So finding good longitudinal data can really help us inform us about our topic. The problem with longitudinal data is it's the same subjects over time, which obviously would be difficult to get. There's also the Perry preschool data, which I've got here on the slide, and they track these kids that went to the Perry preschool some 40 years ago, and they're still tracking them, and they're still using them to inform us about preschool and should we fund it as a society, and what does it do for kids, etc. They say from this study that these Perry kids are more likely to stay in school, they have higher IQs, they earn more money, etc. So, apparently from that study, it's a good idea. Another type of data worthy of mention is something called cross-sectional data. You and I are more likely to collect something called cross-sectional data, and that's I call the Subaru Outback of data, meaning that it's good data. It is really useful for what we need to use it for, but it's not necessarily, the Ferrari of data like, maybe the Audi Quattro would be. So what here we have with cross-sectional data is a single point in time where we collect the same data from a whole bunch of people. We do this lots of times in like the social sciences because we can sample a whole bunch of people at one time. I was recently reading about a study done in Kathmandu about the outbreak of something like a blue-green allergy disorder. And in this case, in order to figure out what was causing it and how to treat it, cross-sectional data was really useful. You didn't necessarily need longitudinal data in a situation like that. So it sort of depends on what you're doing, but cross-sectional data is also very useful. Now I want to just talk a little bit about sampling methods. Now you're going to need to read this in the textbook and understand all these terms because they can get a little bit confusing. So first of all samples should be random in some manner. So simple random sample would be If we wanted to take a study of the people that attend the University of Maine and we literally chose at random, like randomly generated numbers of 100 student numbers, just completely random, where one person has just as much chance of being chosen as the next person. That is what a simple random sample is. It's important to note that it is not always as easy as it might seem to do a simple random sample, or you may start with a simple random sample, but then you go to try to contact these people and you can't contact them all, so then you have to get other ones. So then it isn't a simple random sample. The next type of sampling method that we talk about is the stratified random sample. And here, when we are trying to ensure that we have included an area like the country, within our country, we use this sort of sampling, like the U.S. Census Bureau. Here, we section up the population into mutually exclusive and collectively exhaustive groups called strata. And then each should include randomly selected observations from each stratum. The number of observations per stratum should, of course, be proportional to the stratum size in relationship to its population. So the advantages of something like this would be that these population subdivisions are representative of the population, and the parameter estimates are pretty precise. Now, related to that, or very similar, is this cluster sampling. And clusters are formed by dividing the population into groups like geographic regions and selecting a sample for analysis. And this will work really well if we've got variation within our population groups. So in the stratified sample, we might be using neighborhoods, and we have similar socioeconomic demographics in neighborhoods. But if for some reason we've got a huge mix in our neighborhoods, then cluster sampling might be a little bit better to use. It's a little less precise than other methods, the cluster sampling, but it is useful in applications where the population is concentrated into some natural clusters like city blocks that are not necessarily all one particular demographic. So when we compare the stratified versus the cluster sample, we might want to remember that the sample consists of observations from each group, whereas the cluster sample consists of observations from selected groups. Stratified sampling is preferred if the objective is to increase precision, where cluster sample is preferred if the objective is to reduce our costs. So, of course, we'd want to choose based on, the likelihood of actually being able to do whatever it is we're trying to do. So let's talk a little bit about some of the terms related to all of this sample and these types of things. The first thing is mu. You notice here we've got this word mu written. We know that the expected value of any sample mean should be mu. That's this term, this little U looking thing. We use this pretty commonly whenever we take a huge sample. We expect to be able to calculate the mean, and we call this mean mu. It's just a standard term. In this same sort of sample, we expect that the value of the standard error for this sample mean is going to be computed using the variance. So we're going to first compute the variance, then we're going to take the standard deviation of our variance, and that's going to give us our sample standard deviation, which is very important. And then related to that is the standard error. Sometimes we need to compute a standard error when we have a sample as opposed to a whole population, and to do that we take the standard deviation and we divide it by the square root of n, or the sample size. Now, another thing we know about our normal distribution, another reason we like it so much, is that we can also use it to transform our data into a normal random variable, and we can use that using the z formula that we talked about before on a previous slide or presentation. And just as we did before, but now we have a second option. So our first option, which is here, this is the one we've talked about before, where we take the value we're interested in, we subtract the mean, we divide by the standard deviation. This is really better used if you've got a whole population of data, which you normally don't have. Here, this one over here, we use when we have a sample of our population, because with this one we can account for the standard error. We can use the standard error, which accounts for the sample size. So as our sample becomes really large, then this will eventually approach just the standard deviation of the population. But in the cases where we've got a smaller sample size, this can be very important to use. The reason all this works is because of the central limit theorem. So the central limit theorem says that the sum or the average of a large number of independent observations will approximate a normal distribution. So said differently, what this means is that if we took the shoe size of every single person that attended the University of Maine, and we went out and we measured all their feet and we wrote it down, and we would end up with a huge list of shoe sizes. And we would have, you know, some 12,000 different shoe sizes. And then if we were to graph the shoe size of the people that attended the University of Maine, because we would have such a large sample, what we would find is that it would approximate this thing called a normal distribution, meaning that on average people would have a size, you know, I don't even know, maybe 8 shoe size for women, let's just say, which would mean that the most people, if I'm right about my size 8, if we stacked all the people here, each one of these circles representing a person, the most people would have about a size 8 shoe. Then we'd have, you know, people all the way down here to say a size 4, and people all the way out here to size 12 or something like that. But less people are going to have a size 12 than are going to have a size 4. Most people are going to be probably right here in the middle. So the central limit theorem says that as we gather a larger and larger and larger and larger sample, what happens to our distribution is it starts out maybe a little bit on the flat side. So let me just erase this. We're going to go back and kind of redraw it here. So first thing, if we had a small sample, we'd probably have a distribution that looked like this. We might still have a mean of shoe sizes right around size 8, but it'd be pretty flat on the top because we wouldn't have a very small n, or we wouldn't have a very large n. So this would be for a small n. But then if we went and gathered more shoe sizes, we'd start to see this, where our middle point, and it's actually the standard deviations, they start to shrink in a little bit. So this is kind of a medium size n. And then if we got a huge sample, we would have an n that looked more like, I mean a normal distribution that looked more like this. This is a huge sample size. So the central limit theorem says that this will occur. As our sample size gets larger and larger and larger, our distribution becomes tighter, essentially. So I figured that this concept being as important as it is, it was worthwhile to show you an actual example of how this works. And so what I did was I made a Excel spreadsheet that would randomly generate numbers between 1 and 6 to approximate 3 dice. So my first set of dice rolls was 10 dice rolls. So I randomly generated 3 dice between the numbers 1 and 6, and I added them all up. Let me show you what I'm talking about. So here I have dice 1, dice 2, and dice 3. And in each one of these boxes, I have random between 1 and 6. So it just gives me any random number between 1 and 6, just like rolling a dice would. This is dice 2, this is dice 3. And then I have the sum of the dice rolling over here, which is 14. So when I did this, I did it 10 times. I took an average of this and I got 11.4, which means that if I roll 3 dice 10 times, add them all up, I get an average of 11.4, which means 11.4 is the number that occurs most often, and a standard deviation of, in this case, 2.27. Now you're going to notice that when we get back to the other slides, the numbers are slightly different, and that's because every single time I touch this, the numbers change. So just like that, see how it's different? So every time I change it, the numbers change. And so when I had done it to make up these slides, it had been 11.82 with the standard deviation of almost 4. So now, of course, it's different, but trust me, it changes. So that time there, it was 9.4. And because this is such a small sample, it changes quite a bit. So let's go back to the other slides. And like I said, this is what I got when I did it the first time. So I had, or I don't know, I did it many times, but this is what I ended up with. So I had a mean of 11.82 when I had a small sample of 10, and as I worked my sample larger, I ended up with a mean of 10.37. One thing that is for sure, the consistency certainly gets greater as you have a larger n, that's for sure. But at any rate, you can see here my standard deviation also got smaller, which means the amount of variation around the mean. So I think sometimes I can explain this all day long, but a picture I think is really helpful. So I made these graphs. Now, I just filled the graph lines with random dice. These dice don't really represent the exact numbers that I tossed, but I'm just trying to show you that if we had a histogram with 50 observations, we had a mean of 10.86 with a standard deviation of 3.28. So here's our, on average, is sort of where our mean fell, was kind of right in here, and we have the most, see we have the most observations here. Most of the dice kind of fell in this range of 10 to 13. You can see that there. And that's because we only had 50 observations. But then when we went up to 100 observations, notice our mean now is, so I jumped over, I guess 10, but anyways, the 100 observations, we have a mean of 10.56 with a standard deviation of 2.71. So our standard deviation has dropped down more than a point at this point. And I'm noticing here that this one is slightly different, but again, that's because every time I would redo this, the means would all change, but basically it's pretty darn close. You can see that the majority of the occurrences are still between 10 and 13, but the standard deviation is getting smaller, which means the curve is sort of getting a little tighter. Then on this next one here with 500 observations, our standard deviation, actually I think this is not right, so it should be 2.50 with a mean of 2.37. And again, you can see this sort of pulls up each time. The more observations you have, the tighter the distribution will be. And so the whole idea of the central limit theorem really is that the more observations you have, the tighter the distribution will be, and the more reliable our statistics will be. So in your textbook, I took this picture here of this central limit to kind of illustrate it, if you will. So look over here on this side, we've got the picture that I was trying to draw before. As our n gets larger, notice how our distribution pulls in more, while the smaller n, it is much flatter. Again, very important concept that you wrap your head around at this point. So to illustrate this, I wanted to do a little example. So here, this example is only to show you the impact of the sample size. Okay, so what we have is the pizza diameter is 16 inches and the standard deviation is 0.8 of an inch, right? So we try to always make our pizza 16 inches in diameter, but you know, of course, it's not always perfect. So there's some variation involved, and that's this standard deviation of 0.8. So we want to determine the expected value of the standard error. So that's how much error we can expect when we pick 2, 4, and 9 pizzas randomly. So in this first example here, you see I've got my mu of 16, and I'm taking my standard error, my standard deviation, 0.8, dividing it by square root of 2, and I get 0.57. So this is the amount of variation we would expect when we only draw out 2 pizzas, when we're talking about the amount of variation in the diameter. If we draw out 4 pizzas, notice how this is smaller than 0.57, right? Because now we've got our distribution is becoming more normal as it gets larger. Of course, you know, 4 is not really large enough, but it's moving in the right direction. Then if we wanted to go with 9 pizzas, so we want the expected value of x bar, mu is still going to be 16, then our standard error of x bar will be 0.8 divided by the square root of 9, which is 0.8 divided by 3, which should be about 0.267. So notice how this one is even smaller, right? As our n increases, error of x bar will be 0.8 divided by the square root of 9, which is 0.8 divided by 3, which should be about 0.267. So notice how this one is even smaller, right? As our n increases, our standard error will decrease. Now, to illustrate this a little bit further, let's take this back to our pizzas now. We want to find out what the probability that one randomly selected pizza is actually 15.5 inches or less. You know, we wouldn't want to be ordering a pizza that is actually smaller than its, you know, advertised size. So what is the chances that any pizza out of this same place would be indeed only 15.5 inches or smaller? So what I've done here is I've just written it out. I've got what probability that one randomly selected pizza is 15.5 inches or less. And actually I used this a couple of times, so this sign should actually be or less, and then on the next slide I flip it around. So let's just change this real quick. So here we've got 15.5 minus 16, we get this 0.8. So the value, 0.8 is the standard deviation. This is one randomly selected pizza. So we get this 0.625. We look this up on our Z-chart and we get 0.2643. So this number should actually be a negative 0.0625, right? Because 15 minus 16, that's going to give us a negative number. So we find here our middle point on our table. The midpoint should be 16 inches. And the standard deviation we know is 0.8. So this one here is going to be 16.8 inches, where minus 1 standard deviation is going to be 15.2. So our question is, what's the chances of it being here, which is 15.5 inches or less? We want to know about all this over here. Well, we look up our z value. We find out that it's 0.2643 when we look up our 0.6 on the chart. And what this tells us is that the percent chance of a pizza ending up 15.5 inches or less falls over here on our normal distribution. So I have 25%, that's pretty close, but if you wanted to be more precise, we could put 26%. So there's a 26% chance that our pizza is going to be 15.5 inches or smaller. That's what this is telling us. Now, on this next one, I have the same exact thing, but I'm doing it or greater. So here, now we've got the inequalities facing the correct direction. And now what we want to know is the chances that our pizza is actually going to be here or greater, because we'd much rather have it be greater than 15.5 inches. And what we find out is that we've got a 74% chance that our pizza is going to be greater than 15.5 inches. And we go through the same exact process. So something to take from this is how the question is worded is really important, because if we word the question one way or another, it tells us what we're doing. And that's why I always say draw it out on the little normal distribution. Some people think it's a little bit elementary, but boy, it sure keeps you from making a subtraction error, and subtracting when you shouldn't. Now I have another example that illustrates some of these same points that I think is important, and that is that I pulled the introductory case, and if you read the first page of the chapter, you'll recall that they're talking about having done a marketing campaign to see if people are willing to spend more on their iced coffee. So I guess in general, Starbucks has done an average, and they've found that on average, people have historically been about willing to spend $4.18 on an iced coffee with a standard deviation of 0.84 cents. So they did this huge marketing campaign, and they wanted to see if they could get people to be more willing, to spend a little more on iced coffee than $4.18. So what they want to know is if the campaign is working. And when they took a new sample, they found that people were willing to spend $4.26 on coffee, and they wanted to know if this was actually a change or if it just sort of randomly occurred. So the way I like to approach these sorts of problems, first I like to work out the mechanics. So here we have the mechanics. We plug it into our Z value. I've got all the data up here. So we're going to take our $4.26. This is the value of the new. This is the new mean, or the new average. And we're going to subtract from that the previous average, the one that we're trying to get people to be willing to pay more. And we're going to divide it by the standard deviation, which is 0.84, but we have to make sure we divide that by the square root of 50, because that's the sample size. We sampled 50 people to see if they were willing to pay more. So we go ahead and calculate that out, and we find out that our Z is 0.67. So we take our 0.67, we look that up on our Z table, and we find that 0.67 equates to a Z value of 0.7486. So if we look right here on our table, we know that 0 in this case is represented by $4.18. If we go up one full standard deviation, we've got $4.26. And our value is right about here, and that value that we're comparing is $4 and so we can go ahead and write right on here that we've got our mean. This was our average, or people were generally willing to pay $4.18. Then they did the marketing campaign. Then they went back out and they tried to determine what people were then willing to pay. And our value is about right there, and that is where we would put our $4.26. $4.29 represents a full standard deviation more, taking into account sample size. $4.42 represents 2 standard deviations more. But nonetheless, our value is right here. So what we want to know is our value right here enough different from $4.18 that we can say people actually, after the marketing campaign, are indeed willing to spend more on iced coffee? So we just want to know if this distance is really enough to be certain that people are now willing to spend more on iced coffee after our marketing campaign. So what this tells us is that it is quite possible that in a sample of just 50 customers, that Starbucks could have obtained this new mean of $4.26 in error. And actually, we say that there is a 25% chance that we got this new mean in complete error. Because remember, statistics is all about samples. And if we polled every single person who ever bought a cup of iced coffee, well, then we really wouldn't need to do a statistical test. But because we're just taking a sample of the population, what we want to know is that if our new sample mean is really representative of what we're trying to find out. So this is a really important concept here to kind of get your head around. So what we're trying to determine is $4.26 really sufficiently far away from our mean, this distance right here, to say yes, absolutely, people are now willing to spend more on iced coffee than they were before. But what our little statistical analysis here says is that no, we can't be sure. We cannot be sure people are willing to spend more now on iced coffee after the campaign. Now, related to this is another problem that I made up that's exactly the same, except for I changed the new mean of what people were willing to pay. So now, let's say we did another sample and we found that people were actually willing to pay $4.45 for a cup of iced coffee now, instead of before, where they were only willing to pay $4.26 in the new study. So we'll go about it the same way in that we'll do our z calculation. So we've got z will equal our $4.45 now instead of $4.26. 4.45 minus 4.18 divided by same standard error, 0.84 divided by square root of 50. Now it's just a new study. We still have 50 people. Maybe not the same 50, but still 50 random people. And we're going to find our z value now is 2.269, which means our value falls 2.269 standard deviations away from the mean. So that's going to be about right here. Instead of before, remember it was way over here. So we look up our 2.269 on the z chart, and it's going to be 0.9881, which looks about right based on where I just drew that. So that means that 98% of the time, 98.8% of the time, we can be pretty sure that if we get a new mean of 4.45, that that means that people, yes, are actually willing to spend more on iced coffee than they were before. And we only have now a little less than a 2% or 1.2% chance of error, which is usually is fine in statistics. Because the difference is our mean, what people are willing to pay, is now just a little bit higher. So now we can say that, oh yeah, we're pretty darn certain that people are willing to pay more. So I'm actually going to stop right there in the middle of the chapter, just after finishing section 7.2, because I like to use the last little part of the chapter to give us a nice lead in to what we'll do in the sort of the second part of the semester. So for chapter 7, what you're responsible for then is up through section 2, and these problems that you see listed here, these are what you would need to practice with, and case study 7.1. It's just so important that you really get down the notion of the central limit theorem, how it works, how to compute z values. I want you to spend the time on doing this sort of thing than to take it further into statistical process control. That's important, but I want to make sure you have this down first. So with that in mind, this is the homework assignment for chapter 7, and the next thing you have to look forward to will be the test over the first chapters that we've covered, which essentially are 1, 2, 3, part of chapter 6, and part of chapter 7. So as always, I hope things are going well, and we'll see you soon. Bye.